All right, we're finishing up our method of undetermined coefficients. And so this was our last slide here. And in this, we were just taking a look at some forcing functions, the right-hand side of our differential equation. And we were just trying to figure out what the guess would be for our particular solution. So once you get the guess, right, you would put this back into your differential equation and then try to solve for the constants, the coefficients. And that is called the method of undetermined coefficients. And so it works when the right-hand sides are very nice. And what do we mean by nice? Polynomials, exponentials, sines and cosines, or products of those, of any combination of those three. Good. So let's try to do a full example here from start to finish. So here's our full differential equation. Now how are we going to solve this? It looks like we're going to be solving three different differential equations, right? The homogeneous part of the solution. Then we're going to need to get a particular part for the e to the t. And then we'll keep this together as a polynomial, right? And solve that. So that'll be our three differential equations. So first up is the homogeneous part. Pretty straightforward. We have -1 and -2 as our roots to the characteristic equation. So we get the homogeneous part. So next we go to e to the t. And we would guess a e to the t. Excuse me, and because this exponent is different than these, we don't have to worry about our solution zeroing out on us. So we plug that back into the differential equation. Here's the function, first derivative, second derivative. Add them together, it looks like we get 6a is equal to 1, so 1/6 would be our solution for a. Okay, next we'll go to the polynomial of degree 2. And we'll guess a degree 2 polynomial. And again, we check our homogeneous part of the solution, and that's not part of the polynomial, so we'll continue. Now we plug this into our differential equation by differentiating twice. And so here's our function, here's our first derivative, here's our second derivative. It's put into the differential equation. And now when you're solving stuff like this is a polynomial equal polynomial. And so you assume that this is going to be true for all t, right? And so the best way to solve these kinds of systems is to go through and look at each power of t. So we look at t squared first. And so on the right hand side here, where's our t squared? There's the t squared. We only have one t squared term. And so the 2a on this side has to be equal to the 1 on this side. And so therefore a is 1/2. And now we go to the t terms. The t terms on this side are going to be what? We have a 6a there, 2b there, so 6a plus 2b must be equal to 0, right? And we get b equals -3/2 if I plug in the a equals 1/2 there. Finally, we look at our constants. Excuse me. 2a plus 3b plus 2c must be equal to 2, and so plugging in a and b, we get c. Very good. So now we have our full solution. Here's the homogeneous part. Here's the first particular part. And here's the second particular part. Good. Just as we predicted, right? This works because this is a linear differential equation. All right. So now that we got that technique nailed down, let's take a look at something that might happen. So here's our differential equation. And here's my e to the -d. So what would you guess is the particular solution? We would probably guess, from what we've been doing, that the solution should be a e to the -t, right? Because that's -t, that's -t. Okay, let's plug that into the differential equation and see what we get. So y prime is minus a e to the -t, y double prime is a e to the -t, plugging it in. A minus 3 plus 2 e to the -t, solve for a. Oops, I see I've forgotten an a there. But actually that doesn't matter because, yeah, if you combine these three terms, there's an a missing there again. You get 0 equals e to the -t. Yeah, that's a problem. Okay, and why did that problem come up? Why did this problem come up? What is it if you put in a function and you get 0 out of your left-hand side? That means that this function was the homogeneous part of the homogeneous solution, right? right here. And so, yeah, we have to fix that problem somehow. And so to fix that problem, you multiply your guess by t. So if the original guess for this is homogeneous, then multiply by t to make it not homogeneous, right? And now we plug that function into the differential equation and solve for a. And what do we get? Are we able to solve in this case now? But it looks like the AT terms do cancel out, right? We have an AT there, plus 2AT there, minus 3AT there. So the AT terms cancel out. And so you are just left with the A terms. And so if you solve for those, we just get that A equals 1. Good. And so then here's our full solution then for the differential equation. So the upshot here is that this is the special case. If you have a right-hand side that contains part of the homogeneous solution, so e to the minus t was part of the homogeneous solution right here, we had to multiply by t to get it out of to get something that's not homogeneous. Okay, so let's look at the full method now. So if my right-hand side, my g sub I of t, is a polynomial of degree n, then I guess a polynomial of degree n, but then I multiply by t or t squared, depending on whether or not the polynomial is part of the homogeneous part of the solution. Okay. Similarly, if I have a polynomial of degree n times the exponential function, I want to multiply by the exponential function times a full polynomial of degree n, and then I either multiply by t or t squared if I have to, depending on whether this is part of the homogeneous solution. Similarly, if you have the sine and cosine attached, right, you're going to have a full polynomial of degree n for the cosine, a full polynomial of degree n for the sine. We're going to multiply that by our exponential function, right? The exponential function. And then we multiply that by either nothing or t squared, depending on whether this function is part of the homogeneous solution or not. Okay? Good. So S is either 0, 1, or 2, depending on whether y sub p sub I is part of the homogeneous solution. We're going to see some examples of that. Good. All right. So then once you're finished with your ansatz for your y sub p sub I, you substitute it into the differential equation, and you solve for the coefficients. That's why this method is called the method of undetermined coefficients. Good. All right. So let's take a look at an example. And in these examples, we're not going to actually solve for the coefficients. We're just going to guess what is the form of your ansatz. Okay, so in this case, I've got y double prime minus 3y prime minus 4y equals 3 e to the 2t. What should I guess? You know, my first initial guess would just be a e to the 2t. But then I should check my homogeneous part of the solution, and it looks like that's not going to be a problem. So that is my guess. A e to the 2t would be my guess. And now we're keeping the same roots here so we don't have to keep thinking about them. Cosine of t, don't have to worry about the cosine of t being part of the homogeneous part of the solution. So therefore my guess is a cosine t plus b sine t. Did everybody say that? Okay, similarly, what happens if I have a 6t e to the t sine of 2t? Well, I still have the same homogeneous part, so I don't have to worry about that. The thing to note here, though, is that you have a polynomial of degree 1 times a sine, and so you want a full polynomial of degree 1 for your cosine and a full polynomial of degree 1 for your sine, right, times your e to the t. Those two have to be different. Those two have to be different polynomials of degree 1. Good. How about this one? Y double prime minus y prime minus 2y equals 3t squared. Check the homogeneous roots, 1, minus 1, and 2. I'm clear of polynomials, so therefore my guess is a polynomial of degree 2. Good. And notice that that is a full polynomial of degree 2, right, that we guess. How about the exponential function? E to the 2t. There's a 2 there for your homogeneous part, right? So therefore e to the 2t is going to be part of the homogeneous solution. Therefore, you got to multiply by t. Good. And then how about te to the minus t? Well, I see a minus 1 here, so I need to be careful. Yeah, what's going to happen is that if you just looked at the at plus b e to the minus t, the b e to the minus t is a constant, right? Times e to the minus t, that is part of the homogeneous solution. Therefore, you still have to multiply by t so that each function, the functions I'm talking about now are, if I multiply by t, would be t squared e to the minus t and t e to the minus t, right? Neither of those functions are part of the homogeneous solution, and so we're good. All right. And so similarly, what happens if we have a t to the 2t? So we have a double root. So what is the homogeneous part of the solution here? E to the 2t times c1 plus c2t, right? Isn't that exactly what you would guess? I think so. So if we multiply by t, does that fix everything? So now we have t squared e to the 2t and t e to the 2t as two functions. But that t e to the 2t is still part of the homogeneous part of the solution. So in this case, we had to multiply by t squared. So now we have t cubed e to the 2t, t squared e to the 2t. Neither of those are part of the homogeneous solution. So therefore, that's our final guess. Okay, let's do another one like that. How about y double prime minus y equals 3t plus 5? My roots are 0 and 1. And so notice that e to the 0 is a constant, or number 1, right? So therefore a constant term is part of the homogeneous solution. So therefore I can't just leave it at at plus b, I've got to multiply it by t. Good. And now t squared is not homogeneous and t is not homogeneous, right? Homogeneous part of the solution. Good. And similarly now, if I have y double prime plus 2y prime plus y equals t to the t, sine t 2t, then I look at my roots, minus 1, minus 1. Since I have a sign here, right, that's not going to be part of the homogeneous part of the solution. So I just note here that I have a full polynomial of degree 1 times my sine, full polynomial of degree 1 times my cosine. Very good. All right. How about this one? Y double prime plus 4y. What I wanted to do with this one was to show you, by the way, the homogeneous roots are plus or minus 2i, right? And so therefore sine and cosine are going to be part of the homogeneous solution. So I would initially guess, right, a full polynomial of degree 2 times my sine, full poly of degree 2 times my cosine, right? And then we have to look, since sine of 2t and cosine of 2t are part of the homogeneous solution, I would need to multiply by t. Good. That's the full solution now. That was my full guess. Good. Okay, we've run out of time, so you might take a look at this last one just for fun. The roots are there. Okay, we have to multiply by t. Okay, I'll put these slides up on the class website so you can check them out. Have fun. This is kind of a nice section because it's really a guess and check, develops a little bit of intuition. Okay, see you next time.